I'm here to talk about using finite deterministic automata for string matching. Now, we've already looked at the naive string matching method, the Knopf, Morris and Pratt method for avoiding backtracking, and the Boyer, Moore and Horspool method to reduce comparisons even more and get quite a fast and efficient and practically efficient algorithm. But those all three all have, they all share a problem, which is that they can only match and only work with finite static patterns, and that any kind of ambiguity or infinite or recursion or even just variance is beyond their scope to deal with. And that's where finite deterministic automata come in. Now these are typically defined as pentuples, made up of these five, defined by these five properties, which I will explain now. Firstly, there is a set of states that the automata can be in, and these will correspond to every state that the automata will move into or trying to match as it running through execution. Then there is an initial state, which is obviously a member of the total steps. Then there is an accept state, which is also there are an accept state or multiple accept states, which are a subset of the total states, and are the points in the automata's execution where it will recognise the pattern within the language that it's been given and approve it and accept it. Then there is the alphabet, which will be of symbols, in this case characters, from which languages that the automata may accept or will attempt to accept or recognise can be built. And finally, the transition function, which will be in the size area of the alphabet times the states, because it has, for every state it has to be able to transition to another state or stay where it is, or at least react for every symbol in the alphabet. And that's actually something I'll come back to later, because that is one flaw or one detraction from finite deterministic automata, that when formally defined by specification, they have to be able to respond at each state to any possible symbol in the alphabet, which obviously for large alphabets can be quite a problem and adds a huge deal of overhead and complexity. As an example of what we'll talk about in this short lesson, these represent a small subset of regular expression behaviour, but these are the things I'm going to show how to model with finite deterministic automata. Obviously, there's literal matching, which is obviously just pretty much similar to any of the other string matching methods. Then we start to get some ambiguity and some possibility for recursion with the plus postfix symbol, which we're interpreting as meaning one or more repetitions of the symbol preceding it, and the star, which is 0 or more, and then just the dot, which will be any symbol accepted. Now, here is a simple example of a finite deterministic automata that will match A, B, A plus. And as you can see, here is the language that I'm submitting to it, and it will accept this language. Eventually, it will not match the first 4 characters, but it will match the last 3. And I'll run through its execution on the side in a second. But This is an example of what the automata will look like when drawn as an abstraction outside code. I've highlighted 2 points of interest I'll go to later. But basically converting that into code, you will basically, for the naive approach to string matching converted to this form, you will basically have a loop trying to match it and controlling the state, and we keep on recurring to the transition function. So a continuous loop until either their language has been exhausted and will be rejected as a whole, or until a sex state is accepted, or depending on the purpose of the search function, the sep state is accepted and there's no more symbols to process. Now, as you can see, in this path of execution, we're starting at an initial state which is meaningless in regards to the pattern I've just designated 0 here, and as each symbol is read, the initial state will be replaced by the transition function into a new state. As you can see, passing through the first 4, we move to A, but then we move to AB, but then we can't move any further, and we're actually thrown back. In this case, I've named the states in relation to the pattern. That's just something I've done for ease of human recognition. They can be named anything or have any representation. But you can see after we've got here, after the first 4 symbols, then the pattern can recognise the last 3 as the pattern, and if the language kept on repeating A, it would also still recognise it. And as you can see, I've highlighted B there because this is quite interesting, because if without this, the deterministic finite automata would just be modelling the naive method. But I'm showing that although it's hard to get this by automative procedure and automatically generate finite automata by hand or by particularly clever algorithms, you can implement automata which do try and eliminate backtracking, and so can emulate more advanced and more efficient algorithms. Which is why for most finite automata, the big O, the worst case complexity of matching, is basically n, but that can be improved. I'll talk about complexity and the pre-generation later. But I'll talk about the star and the dot symbol here. The star is very easy to model with automata. It just means it's just a case of maintaining the state. However, a problem with finite deterministic automata, which can be addressed by using other models of computation, such as non-deterministic finite automata, is that with an ambiguous symbol, such as the dot, you have to split off, which can basically lead to an exponential growth of states. Now, this can often be optimised away by hand, but it's very hard to do it automatically. But again, I haven't written down the execution for here just for time, but you can see that automata will accept the pattern there, and also, but it also has to include a lot of cases to reject it as well, which is another flaw of, well, not necessarily a flaw, but is another thing which can lead to inefficiency and extra overhead of code and complexity with deterministic finite automata. And interesting, you can see there are 2 accept states here, because it has to accept the pattern A, any number of A's, B, or any number of B's, B or A, B, B, because of the ambiguity introduced by the dot character. And basically, that's just going over it very briefly, but that's scratching the surface of finite or deterministic finite automata for string matching. And I think that's a good way to look at the beginning, because basically you would only use them to get sort of the ambiguity in regular expression behavior, because typically they're quite expensive to set up in the beginning, because the transition function, as I said earlier, is the alphabet, the whole alphabet, which can be which in most cases would be quite large. It would be at least 26, but probably more in practicality, times the constant arbitrary to the machine, and then the expected runtime would average only be n. So it's wouldn't be your first choice if you had other options, but it is quite a good, quite easy and simple to implement way of getting that complex ambiguity and behavior that you can't get from other string matching methods. I briefly talked about how other variances of this computation model, such as non-deterministic finite automata, can be used to model the behavior I've shown and the more complex regular expression functions. And that is basically all I'm doing now, because I have an exam tomorrow. Thanks.